Before we studied how to solve the given different ordinary differential equation numerically. In this unit, we will try to learn how to solve the given PDE numerically. In case of ODE, same standard method can be used to solve all types of OD, but in case of PD, we cannot do that. Hence, it is very essential to classify the PDE. So let us start the classification of PDE. Let us consider a linear second order PDE of the form a dou square u by dou x square plus b dou square u by dou x dou y plus c dou square u by dou y square plus d dou u by dou x plus e dou u by dou y plus f u equal to 0. That is a uxx plus b uxy plus c uyy plus d ux plus e uy plus f of u equal to 0, where the coefficients A, B, C, D, E and F are either constants or functions of x and y. Then let us classify this field. Let us name it as equation 1. So let us classify the equation 1. In order to classify the equation 1, we will follow the following steps. So first one is, if b square minus 4ac is less than 0 for all x and y, then the given PDE is called elliptic PDE. Case 2 is, if b square minus 4ac is equal to 0 for all x and y, then it is called parabolic Case 3, if b square minus 4ac is greater than 0 for all x and y, it is called hyperbolic. For example, Example 1. Let us consider classify the PDE uxx plus uyy equal to 0. So we know this is a Laplace equation. Why I am giving this example means in our course we will try to solve the Laplace equation numerically. So that's why I am starting with the example of Laplace equation. Now here you can say a equal to 1, b equal to 0, c equal to 1, and D, E, F all are 0. Here A means the coefficient of uxx, B means coefficient of uxy which is not available here, and C means the coefficient of uyy. So now you put here b square minus 4ac. So b square is 0 square minus 4 into a is 1 into c is 1, and so that is equal minus 4, which is less than 0. Therefore Laplace equation is elliptic PDE. Example 2. Let us classify the heat equation ut is equal to c square uxx. So which is nothing but heat equation, Now let us find out what are the values of a, b and c. So now if we find out the coefficients here, we will find that a equal to 0, b equal to 0, and c equal to minus c square. You can write this one as ut minus c square uxx equal to 0. So coefficient of utt we can consider as a coefficient of uxt will be b, and coefficient of uxx will be c. Here coefficient of utt is not there, coefficient of uxt is not there, only coefficient of uxx is there, and so we will consider it as minus c square. But in other way also you can take a equal to minus c square, b equal to 0, and c equal to 0. In both the case you will get the same results. So let us consider in this way, and b square minus 4ac is equal to 0 square minus 4 into 0 into minus c square, and which is nothing but 0. Hence it is a parabolic PDE. It is a parabolic PDE. Now let me take another example. Example 3. Let me classify the wave equation UTT is equal to something k square uxx. This is known as wave equation. So we can write it as UTT minus k square uxx equal to 0. Now here a equal to 1, b equal to 0, and c equal to minus k square, and so b square minus 4ac is equal to 0 square minus 4 into 1 into minus k square, and so which is nothing but 4k square, which is always positive, and hence it is hyperbolic. It is hyperbolic PD. Here I would like to say one thing. If a b c d e f are all are constant, then the pd will behaves the behavior of the pd will remain same throughout the xy plane. But if a b c are functions of x and y, the same pd may behave differently in different region of the xy plane. For example, suppose I will give you an example. The pde classify the pde xuxx plus uyy equal to 0. Now a equal to x, b equal to 0, c equal to 1. So b square minus 4ac is equal to 0 square minus 4 into x into 1. So minus 4x. So we cannot say this is always less than 0. Depending upon the nature of x, we can decide the sign of the value of b square minus 4ax, 4ac. So now if x is greater than 0, then b square minus 4ac, which is minus 4x, is always less than 0. Therefore it is elliptic. If x is less than 0, then minus 4x will be greater than 0, and as a result we can say b square minus 4ac is greater than 0. Therefore it is hyperbolic PDE. If x is 0, then b square minus 4ac equal to 0, which represents the parabolic PD. So for x greater than 0, that means the right half of the plane, in the right half of the plane the PD behaves like your elliptic PD, and for the left half x is less than 0, the PD behaves as hyperbolic PD, but at x equal to 0 it is the parabolic PDE. So from there it is clear that if the coefficient of uxx, uyy, uxy are functions of x and y, then the nature of the PD changes in each and every region of the xy plane. Let me give another example here. Classify the given PDE x square fxx plus 1 minus y square fyy is equal to 0. Now here a equal to x square, b equal to 0, c equal to 1 minus y square. So here I am giving you the example where everywhere you can see b is 0, but it is not necessarily always b equal to 0. I am giving this example to make you understand. So if b is non-zero, you have to put that value in the expression and you have to decide the nature of the PD. So in the given PD we have the coefficients a, b, c as x square, b is 0, c is 1 minus y square. Now b square minus 4ac, 0 square minus 4 into x square into 1 minus y square. Let us discuss the behavior of this PD. Now you see x square is always positive, whatever value of x it may be except x equal to 0. So the nature of the PD remains same for any value of x except at 0. So let me consider first for x equal to 0. At x equal to 0, what is the nature of the PD? Let me check. If I put x equal to 0 here, b square minus 4ac is equal to 0 square minus 4 into 0 into 1 minus y square, and that is equal to 0, which is nothing but parabolic PD. Okay, so let us take the second part. Here I am not giving any possibility of x, because if I take x negative, still x square positive. If I take x positive, still x square positive. So there will be no change at all in the behavior of the PD for positive x and negative x. So for x equal to 0, we got the nature of the PD, and it is nothing but parabolic. Now let us go for the variable y. So we think that b square minus 4ac is equal to minus 4x square into 1 minus y square. So what will happen to the PD if y square is greater than 1, and what will happen to the PD if y square is less than 1? If we are able to decide those two natures, then our job is over. So now let y square is greater than 1. Y square is greater than 1 means this will be a negative thing, and so negative into negative it will be positive. So if y square is greater than 1, that means y is less than minus 1 and y is greater than 1. So these are the two intervals. For those two cases, whatever value of x it may be, for every x except x is not equal to 0. If x equal to 0, it will be parabolic. So for non-zero x and y square greater than 1, but the nature will be b square minus 4ac will be greater than 0. And so this is a hyperbolic PD. For y square greater than 1 or y less than minus 1 and y greater than 1, the given PD behaves like a hyperbolic PD. Now suppose y square is less than 1. Y square is less than 1 means this bracket 1 minus y square will be positive, and so here there will be no change in the sign, so it will be a negative values. So b square minus 4ac will be less than 0, and y square less than 1 for every x non-zero. You don't forget to write for every x, because x may be any value. We are considering only the nature of y, and so but one restriction we are putting on x, that is x should not be 0. So for any value of x, except x equal to 0, if y square is less than 1, b square minus 4ac will be less than 0, and this represents an elliptic PD. So like this, if from here we knew that if the coefficients a, b, c are functions of x and y, the nature of the PDs varies from region to region. But if a, b, c are constants, then the nature of the PD remains same throughout the region of xy plane. Another thing you should remember here, this this classification is only for second order PD, not any other PD. So, and here you remember the second order PD which is linear, that only our point of discussion. So with this, today I stop my lecture.